He's a professor at the University of Washington. He's a long-term visitor here in CITA into December. So his research basically focused on numerical simulation on various different scales, from the structural formation of the universe to the solar system planets. So let's welcome let's talk about mathematics and baryons.
Yeah, thank you. Thank you for having me here and letting me visit for a while. Thank you for coming. So I'm going to talk about dark matter, but the theme, of course, as I say, is that when you're studying dark matter, it's important to remember the baryons. The other way I want to say, by way of introduction, that this work wouldn't be accomplished if it wasn't for all my collaborators. So at the University of Washington, we have this thing called the N-body shop, so focusing on N-body simulations of various size-scale objects. The work I'm going to be talking about today is mostly by my current and former graduate students, which I've highlighted in bold, but it's also a cast of thousands has been involved, and I've actually left some people off. So what I'm going to talk about, I'm just going to give a little short motivation, which I think would be appropriate for this audience, and then talk about the baryon physics that I do include, and then I'm going to have two sections. First, talking about self-interacting dark matter and how that plays out once you include the effects of star formation. And then second, I'm going to talk about axion dark matter, particularly talking about the QCD variety of axion dark matter. Right, so the motivation, right? Well, first, this is the picture from Planck. The various cosmological constraints indicate that all but 5% of the energy density in the universe is stuff we don't know about, things that are not part of the standard model of particle physics. And furthermore, about all we know both the dark matter and the dark energy is its gravitational properties.
What are the constraints on machos? So you're saying that it's not part of the solid model, but what is?
So I guess the main constraint on machos is at some point, like during at the epoch of the CMB, right? Either they'd still have to be machos, or, right, if they were uniform then, they would have affected the cosmic microwave background. I think that's right. This dark matter is fairly tightly constrained by the cosmic microwave background, as well as sort of local measurements. Yeah, is that?
There's also a mass gap in the requirements, right?
There's a
mass gap where you can have black holes of, say, a few Earth masses or Jupiter masses, which could make up all the dark matter without violating any constraints.
Well, first of all, it's a question of whether black holes are baryons or not. But there was that debate with Stephen Hawking and others. No, but the point I'm making is that, right, they'd still have to be they'd have to be primordial, is the point I'm making about the cosmic microwave background. So, yeah, possibly primordial black holes, although that would be kind of strange, but a possibility. That brings up that, right, we know very little about this. One thing I'd like to point out is that, back in the 80s, the first candidate for this stuff was a standard model particle, a neutrino, and those numerical simulations with all of 32,000 particles, ruled out the standard neutrinos because we couldn't have top-down formation of large-scale structure. So that was that ruled out standard neutrinos, but that leaves, there possibly could be a heavy neutrino, KeV or heavier, and a couple of other candidates include axions of several types. Probably the candidate most people talk about these days are some sort of weakly interacting massive particle, such as the lightest supersymmetric particle. But I want to point out that even though the baryons are only 5%, they're still very important. I mean, some of my best friends are baryons, right? So we need to really pay attention to them.
Some of your worst enemies.
Yes, and some of my worst enemies are baryons, yeah. Okay, so first let me talk about this effect in terms of the dwarf galaxies. And this is actually work from a little while ago by Alex Fry and our group, and looking at the effect of self-interacting dark matter in particular dwarf galaxies. And the idea is if you have self-interacting dark matter, we'd be able to take, say, the NFW profile, and the interactions would flatten that inner core. And if you look at this figure, and let's first focus on the dashed lines, we can compare a couple of halos run with only cold dark matter. This one is roughly a 50 kilometer per second halo dwarfish galaxy, and then this halo is actually a 30 kilometer per second, so a very small halo. If you run them in CDM, you get this cuspy inner profile in the central kiloparsec. If you run them with self-interacting dark matter, here a cross-section of 2 centimeters squared per gram, that interaction flattens the cores to these dashed lines here. And this effect was why it was first invoked back in 2001 or so. But then what happens if you add the baryons, right, we have baryonic physics, you have star formation, and then there's this effect if you have bursty star formation. The motions of the gas and the stars from supernova feedback interacts with the dark matter and is a heating mechanism, and that can also flatten the core. So if we look at now the solid version of these lines and compare, well, let's look at the 50 kilometers per second dwarf as first off. So I compare running with CDM and baryons or self-interacting dark matter and baryons. We see that the core is flattened significantly in both cases. So because of the baryonic effects are also flattening the halo. In fact, with this, in this mass range is actually doing it more effectively than the self-interacting dark matter. It's very hard to tell the difference between the two models. Okay. It's a little more interesting if we go to very small galaxies, then there isn't that much star formation. And so the prediction is that if it is self-interacting dark matter, we could go to very low mass halos, and we would actually, so compare the green with magenta solid lines, there would be an observable effect because we're at such low mass, the star formation is very inefficient. The unfortunate thing, of course, is that there aren't many stars to actually observe. So actually finding such objects and measuring is difficult. But nevertheless, in order to really test the self-interacting dark matter, we should be looking at the very low mass galaxies. Yeah?
I guess I don't understand.
Oh, sorry. How about in front first?
I don't understand what self-interacting dark matter means. Doesn't that mean dissipation? So why would that flatten the...
No, so, yeah, I should have explained. I'm sorry. So by self-interacting dark matter, there is some cross-section for interaction of the dark matter with itself, but not with the standard model.
So that means
And that interaction is elastic. So there is no energy is conserved.
So why would it flatten the profile then if it's elastic?
So it's essentially a way, because it can, make sure I explain this right, because it can actually interact, there's a way of transporting heat.
So my question
Yeah.
is related to this, that you add a point mass at the center.
Mm-hmm.
That's in the case of stellar interactions, you tend to want to cusp.
Yes.
So if you had a point mass, you then actually have dark matter forming a cusp with stellar interaction.
So, right, so if you're, I'm actually going to show something like this happening. Yes, if you just add, say, a black hole
Yeah.
to the center of a galaxy, the dark matter would contract and form something more cuspy.
But so with the stars, so you can actually try to trace that again.
Yeah, the stars would do the same thing.
Of course, that would
Yeah, actually, that's another thing about this is that this sort of heating effect by the baryonic physics will also core out the stellar distribution, and this is something to look for. But that's another topic, but although an interesting one.
I think Chris interrupted. You were trying to explain why is it flattened when you have elastic scattering. Is there an easy explanation for that?
I'll probably get it wrong, but it's essentially you are allowing the particles in the center of the galaxy to be heated up by this interaction. As their velocity dispersion gets larger, their cuspiness gets smaller.
Is it something to do with the radio orbits become smaller?
Well, that would happen, right? The orbits would isotropize. I don't think that's the main effect, though.
M over R is converging towards small r in a NFW profile. And so potentially
Yeah.
it's very fragile, right?
Yeah. True.
It's very shallow, which is, so if you have higher velocity dispersion, dark matter particles on the side, that would tend to heat the core.
So normally in an NFW profile, you actually have decreasing velocity dispersion as you go to the center. If you make that velocity dispersion flat, sorry, I'm doing it the wrong way. The velocity dispersion is actually going down as you go towards the center in this kind of halo. The interactions will now make that velocity dispersion flat, therefore raising the central velocity dispersion and thereby flattening the cusp.
Since they're interacting with it, shouldn't the solution here converge to a polytrope? So you should, in a polytrope, you get...
Should converge, right, that's a good question. If you let this run long enough, you should end up with a singular isothermal sphere. So the cusp will go up again.
But this might explain why you get a flat, where it's flat in the center. Because the polytrope is flat, but it has a flat density in the center.
It depends on the index of the polytrope.
Oh, well, so here it's like 3 halves. So polytropic index of 3 half, right? If you don't have any other degrees of freedom.
Yeah, well, why is it 3 halves? Like I say, the
Each particle has 3 degrees of freedom. So you have 3 halves.
if it fully conducts, then you'd have isothermal. Isothermal goes as r to the minus 2. All right. So a polytropic index of infinity. All right.
Yeah, but of that? If it's
I think,
Well, it depends on
but-
the boundary condition.
Yeah.
The isothermal everywhere.
yeah, well, infinite.
Where there's no interaction over the edge of the universe.
no, but you need a way to get rid of it. So sorry, interrupt you.
Yeah. Well, let's move on. Yeah, let's move on. Yeah. Let's move on. This is meant to be just an introduction, but it is interesting. So I want to move on to the kinds of simulations we've been doing with the baryons. You guys have seen this slide from the Jamboree. So we have star formation and supernova feedback, but a key ingredient of some of the simulations I'll be showing is the black hole feedback. So we have a number of simulations, which we call Romulus 25, what I call barely cosmological volume, uniformly sampled with roughly 10 to the 5 solar mass resolution in both the dark matter and the baryons. Gravitational resolution of 1/4 of a kiloparsec. So we have a volume of these simulations that has, well, of order of a dozen Milky Way galaxies, more like 50 Milky Way mass type galaxies. And with the exact same physics, we also run a cluster, a Virgo-sized cluster. I could talk more about the cluster, but that would be another seminar. I'll be focusing mainly on the Romulus 25.
So the cluster simulation is a constrained simulation without periodic boundary conditions.
No, it's a sample that was drawn from ran a uniform volume, drew a Virgo-sized cluster, in dark matter, and then re-simulated using our usual zoom-in technique, where you have the adapted resolution in the Lagrangian region from which the cluster forms.
So the overall fundamental model is not set by two.
No, yeah, so this was drawn from a larger volume. So 50 megaparsecs, still kind of small, but yeah.
And you've got the waves on the large volume.
Yes. Yeah, really keep all the waves. So key ingredients here is our sort of the novel thing about these things is we form black holes. Actually, let me go to the other slide rather than a splash slide. And we're motivated by the fact that when we were running a large Milky Way size and above galaxies, particularly the central regions, were not effectively, did not have their star formation effectively suppressed, and we get runaway star formation in the center. We saw, conveniently, that's where a supermassive black hole is, and we form a black hole basically if we have low metallicity, very dense gas. So the key thing, it's local formation criteria, and then they grow from the accreting gas according to roughly a Bondi Hoyle formula, and then release energy. Another thing is that we wanted to be able to track the merging of supermassive black holes. And so two things we do, that's why we have the relatively high resolution in the dark matter, so that the black holes aren't scattered by the heavier dark matter particles. And we also, to account for essentially unresolved dynamical friction, we include a Chandrasekhar formula for sinking of a black hole off the dark matter.
But that is not really necessary, right? If your black hole is 10 to the 6 solar masses and your dark matter particle 10 to the 5.
There's still a gap there of the sort of, right? You'd want the dark matter to be even lower mass.
Have you checked that convergence?
Yeah.
So what would you need to maybe just go on?
Okay, I'd have to look at Alex's thesis. I don't know. Probably another order of magnitude. Yeah. Yeah. And so we've been successful at reproducing things like the stellar mass. So this is the stellar mass to halo mass ratio as a function of the halo mass running from dwarf galaxies all the way up to small groups, 10 to the 13, falling on the Moster relation, right? And right, this is essentially the black holes doing their thing, suppressing star formation at high mass. And then what's going on here is these guys are actually, it's not that their stellar mass is high, it's their dark matter mass is low, right? So these are satellite halos with relative, where the dark matter has been stripped away. And for the cluster, we've gone up to, right, the central galaxy of that cluster sits in 10 to the 14 solar masses, and a little less than 10 to the 12 solar masses in stars. It's a little above the line, but you know, doing pretty well at getting this would be the brightest cluster galaxy in that cluster. So we're reasonably happy with that, with this prescription. And
These other points are data or simulation?
these points are data. Yeah. And so we ran another series of simulations. We call it the genetically modified simulation. So we're looking at the effect of the physics and the dark matter on Milky Way-sized galaxies. And we wanted a series of galaxies that were close to the same with just slightly different merger histories. And so we changed essentially the mass of a late merger by changing the initial conditions. And this is a technique that Andrew Ponson developed, very similar to, it was quite a while ago, Yehuda Hoffman had a similar technique. And so this is a galaxy that's picked out of a 50 megaparsec box. It's got the same kind of, same mass resolution that I talked about before, blast wave star formation and feedback, going back to Greg Stinson's work, and I've already talked about the black hole. And so we're going to run these both in cold dark matter and in self-interacting dark matter with the cross-section given there. So first let me just talk about the CDM runs. And this is work. So the question mark here is, I'm going to check my email when I finish the talk to see if Nicole has submitted the paper yet. But it's to be submitted imminently by Nicole Sanchez. Her main work has been on the CGM, but we've got these simulations, and let's take a look at them. So here's a star formation history of a series of galaxies. This is patient 0. And we've modified, again, the size of one of the satellites coming in. And as we modify the satellite, we get this interesting, the merger happens at about this time. And so depending on the size of the merger, we get this change in star formation history from galaxies that continue to form stars to galaxies that are quenched. The details of what is causing the quenching are not clear, except for the fact that it is definitely tied to the central black hole. Because if we run the same thing without a black hole, we find that we don't get the quenching.
So how big is this?
This is the Milky Way, so a little less than 10 to the 12 solar mass halo. Right, the evidence also comes from the accretion rate of the black hole over time. At that point when the galaxy quenches, or right before, the two runs that quenched have this bump in the black hole accretion rate, which seems to be correlated with when the star formation shuts off.
So are we just removing the disk, or did you look to see?
There's still gas in the disk. Certainly in the central region, it's been effectively evacuated.
Central meaning like 10 kiloparsecs?
No, the few kiloparsecs. No, 10 kiloparsecs is essentially the size of the disk.
Right.
Yeah, so the bulge area has been. This is still being worked on, so yeah, I don't know all the details. So now let's redo some of this with self-interacting dark matter. And first of all, these are dark matter only runs, all right? And these are behaving as advertised. The density is a function of radius. In cold dark matter is cuspy. You turn on the self-interactions and it flattens out. So what happens if we look at this as and add the baryons? Okay, so this is, let me clear what I'm plotting here. This is the density of the dark matter in a simulation that includes the baryonic physics. Okay, and we see that if we have the cold dark matter is a solid, the self-interacting dark matter is actually more cuspy. Now, that's kind of strange. So what's going on there? Well, it becomes a little clearer when you look at the total density. Okay, and all right, and let's remind ourselves. So we got a factor of a little less than 2 here. But if we look at the total density, there's more a factor of 3 or 4 gap here. And so it's clear as what happened is that the baryons are now more essentially concentrated in the self-interacting dark matter simulation. And what's that doing? Then you have, somebody, Chris mentioned, you have an adiabatic contraction. The dark matter is becoming more contracted because it's falling into the potential well of the baryons. And, you know, we're running, right? I'm supposed to finish at 4, right?
Or even after.
Okay. So, well, yeah, we can, this is really quick. So if you look at the star formation history, this was GM3 in the previous paper, but so the cold dark matter star formation history is way down here. The star formation history with the self-interacting dark matter has this huge spike. So again, well, how's self-interacting dark matter? Still not completely clear, but if we look at the morphology of what's going on in the center, with the cold dark matter, we got this, and notice the scale here, this is 5 kiloparsecs. So the very central regions, nice and uniform. Over here, what's going on? We've got this bar formation. So this is all preliminary. The idea here is if you have a flat central density, right, that's harmonic. And it's very unstable to bar formation. And that's what the simulation seems to indicate. You have strong bar formation that enhances star formation greatly. Great flow of material into the center. And so you get the non-intuitive result that flattening the dark matter actually significantly makes the total profile more cuspy.
Does this include black hole feedback?
Yes, this does include black hole feedback, yeah.
So you put in as much feedback as you get away with, and it doesn't.
Yeah, yeah. And then speaking of black holes, right, again, this is preliminary. The black holes, their merger rate also depends on them pulling around material, right? It's not just the black hole, it's the black hole plus the rest of the material they're holding on to, stars and dark matter, and we're looking at the merger rates of the black holes as a function of time, and the lack of cuspy dark matter means that the merger rates for the SIDM black holes are suppressed compared to the CDM. Again, we're still sort of analyzing all this stuff, but right, again, here, the takeaway here is that, right, initially we see that they have similar effects, but we have these nonlinear interactions between the potential of the dark matter and the baryonic physics that is non-obvious and sort of overwhelms what we initially talked about before. Particularly, all right, we're focusing on Milky Way-sized galaxies now.